Okay, so
Hi,
let me
Colin.
point out some potential pitfalls, okay? And this is a wonderful equation, I equals mr squared.
Beautiful.
It's like the branch that all of these equations come from. But to purely use mr squared is only under two very, very, very special circumstances. You're told that it's a thin hoop or it's a point mass, okay? Anything else, solid cylinder, hollow cylinder, solid sphere, whatever it is, you have to find the moment of inertia equation. There's some on the lecture notes, there's also some on page 210 in your book, okay? So get out of the idea that mr squared, oh, I'm only going to use mr squared.
Just so I-
mr squared is actually very rarely used, but it forms the basis of everything else, okay? So all the other equations branch from this mr squared idea. You get to Calc 3, that's usually where you drive all those other equations. Okay, so both of your answers, like on 1 and 2, should be something times 10 to the negative third. Pay attention to the fact that I have given you in all of this data 3 digits. So help me, if you just write 5 times 10 to the negative third for problem number 1, if you just have that answer, you're doing me a disservice, because I gave you 3 significant digits and you give me 1 significant digit. What?
Because it's exactly 0.005, if we write 0.005, is that acceptable?
0.005 only
the-
has 1 significant digit. These zeros don't count.
Fine.
I'm just telling you, this is how science is done. You don't start counting until you hit the first non-zero digit. Now, if you want to put 2 zeros on the other side of that, cool, okay? It's just easier if you do it in scientific notation, because the beauty of scientific notation, everything that's there is significant. Okay. 5 through 10.
Ooh, my sig figs are really bad on this one.
Oh, yeah. Notice again, you have 3 significant digits in every number that I gave you. Every answer should have 3 significant digits. So, because if 5 is wrong, everything is going to be wrong. Your answer to 5 should be around 0.4.
Okay.
Okay?
Yeah, close enough.
That's going to be around 0.4. Now, on number 7, when you want to find that angular acceleration, do not do this. Do not go, oh, I can use F equals ma, because I know the force, I know the mass, I can find the acceleration, and then plug that into A equals R alpha. Horrible. Stop. Don't. Okay? Yeah. Don't. You cannot use F equals ma on things that spin. And the reason being is because where you apply that force
Torque equals I fish.
greatly alters the acceleration of the system. Okay? So that's why you cannot use F equals ma. So anyway, so all of this kind of builds on each other. So when you get down to number 10, if this whole thing goes well, your answer to number 10 should be between 5 and 600. Preston,
I'm double.
are we not in that realm? Okay. Here's a little check. Your answer to number 8 should be around 100.
Oh, I just screwed up math somewhere.
Well, if
Okay.
something's gonna be wrong, then eight's gonna be wrong.
Now let's talk about 14 and 15. Because I promise you, you're going to have a question like 14 and 15 on the test on Tuesday. Okay? Promise you, you're going to have a question like this. So here's the idea on number 14. Okay? You want to find the angular momentum. So to find the angular momentum, you need 2 things. You need I and omega. Okay? 2 things that you need. So in this situation, your omega, you got to take the 30 revolutions per minute, again, which has 3 significant digits, and change that into radians per second, which should be, oddly enough, about 3.14 radians per second. Okay? Then on your I, and I told you, I gave you the equation for the moment of inertia, 2/3 mr squared. So that overall angular momentum when you get done, should be something times 10 to the negative fifth.
That's a good
It
thing.
should start with a 4 and be 10 to the negative fifth. Okay? Cool with that?
Yup.
Cool. Now, when you get to 15, just like linear momentum is conserved, angular momentum has to be conserved. So you're going to start, you have two things. You have the ball and you have the bug. So start off and go with I of the ball, eyeball, or L of the ball, plus L of the bug equals L prime of the ball plus L prime of the bug. If it was linear momentum, you would have momentum of the ball plus momentum of the bug. It's the same idea. Now, conveniently, the bug isn't part of the system. Okay, so that goes away. We don't have to worry about that. That's not part of the story.
Did I forget?
So, the L of the ball, which you found on number 15, you already have that number. You don't need to recalculate. You already know what that is. Okay? Now, over here, because here's your spinning ball, and the bug lands on it, and that's spinning together. So this whole thing is one system. So they're going to be spinning at the same rate. Okay? So over here, you can factor out that new velocity. So this is going to be the eyeball plus the eyebug times
2W.
omega prime. Okay?
Oh yeah, I'm stupid.
Now, you found the moment of inertia of the ball up in number 14. You already have that number. You found it. Okay? The eye of the bug, you're going to use mr squared. And you're going to use mr squared because it's a point mass of the bug. It's a point mass sitting on that ball that's spinning. So you've got the mass of the ball. The radius is just going to be the radius of
The sphere.
the sphere because that's what it's on. Okay? So now, think about this. On number 14, it was spinning at 3.14 radians per second. What do you know about your answer to 15?
It should
Is it
be-
going to be bigger or smaller than 3.14?
Smaller.
It's got to be smaller. It's just like when two objects collide and they move off, like a California problem. It slows down because you've increased the mass. This one, we've increased the moment of inertia, so it has to spin slower. So your answer to 15 would make a not so good GPA.
My current number is a not so good GPA,
I made a
but I did a dumb and forgot the square number.
silly. This is then
Whoa.
that.
Plus P 1 point.
Yeah, Sean, how we doing?
To the negative fifth.
You're definitely not supposed to be in like 10 to the negative third on number 15, right?
For your answer?
Yeah.
Oh, God, no.
Mm-mm.
Oh, God, no. What do you have for your answer to 14?
4.52 times 10 to the negative fifth.
Perfect.
Okay.
No wonder I did it.
I'm guessing you might have screwed up the one of that. What do you have for the moment of inertia of the bug?
Oh. I just don't have anything.
What? I don't have anything. I don't. What do you have for the moment of inertia for the bug? Nothing.
What?
Nothing.
At least that's what I'm somewhat confident.
Wait, so how did you get a different
Don't
number?
ask. No one knows. Now I plug this in, and we. Oh.
Colin, you don't see this.
Tell me
but
what
he's
number
making
you get
hand
so I
movements.
know I did math right.
Okay.
Because I forgot to square it.
On number 16, where you're finding the moment of inertia of the moon,
Oh,
that's going to be a really, 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 really big number.
Like 10 to the 34th big?
10 to the 34th big.
bet.
Okay?
Yes.
So again, you're going to use L equals I omega. In this situation, you're going to use mr squared because you're told to treat the moon as a point mass. okay, which it is. And then you've got to find your omega. I tell you that it takes 27.3 days. Now, as the moon goes around in its orbit, which is drawn like this, but that isn't really how it goes, but just stay with me. So there's the moon, or the earth, and it's going around like this. How many radians is it going to move through, Danny? When it makes one revolution around the earth?
2.
Pi.
Pi.
Yeah.
So that's going to be 2 pi divided by the number of seconds in 27.3 days. So yes, your answer to 16 should be something times 10 to the 34th.
Sweet.
Okay? Now, on 17, let's talk about 17. So, you got a 5 kilogram cylinder, 7.3 radians per second. I was nice, I already gave it to you in radians per second.
I got 2.51.
And you're going to apply a torque to it, the outside edge for 5 seconds. By how much does the angular momentum change? Okay? So, there's a couple of ways that you can do this problem. So, if you like visuals, you can say, okay, so you know that it's a solid cylinder. So you know your I is going to be 1/2 mr squared. Okay, so you can find the moment of inertia and all this good stuff. And then you know how fast it's initially spinning. So you can find that initial value of the angular momentum. Okay, you can do that. It's cool. Okay. Then you're told that I'm applying a torque of 0.04 newtons. Now, you know that torque equals two things. Torque equals force times radius, and it equals I alpha. Okay? So, if you know the force and the radius, and you know the moment of inertia, then you can determine the acceleration of the object. Okay? Cool. Now you know how much it's going to accelerate. Then you can go, okay, once you get that, then you go, okay, omega equals omega naught plus alpha time. So you know how fast it's spinning at the beginning, that 3.70. You're going to take that acceleration and you know the time. And then you find the new angular velocity, which oddly enough has to be bigger than 3.70 because of the fact that it's speeding up. Okay? So now you have the new angular velocity. So then you can find the new angular momentum by taking that same I, that 1/2 mr squared, times that new rate of spin. Okay? Then you find your new angular momentum, subtract that from the original momentum. There you go. So that works. It's smash mouth physics. Okay? And it works. Okay? Now your other option is that you can use that equation that we talked about yesterday, that you're changing your angular momentum equals torque times time. Okay? So here's the other way you can do it. So you know how much torque is applied. Yep, 0.04 Newton meters. You know how long it's applied. You can do it that way too. So you can either find the original angular momentum, then find the final angular momentum and subtract those two, or you can just use this. But your answer should be very much less than 1.
Oh. That's a weird gap.
Between 0 and 1,
Okay, yeah, it is a good gap. Like,
closer to 0.
yeah, good there. Yeah.
Okay? Closer to 0. On the book problems,
Oh,
Here-
momentum. Okay.
answer to 40 should start with a 4.
Oh, wait. I did something bad and dumb.
Bad and dumb. We're back to that story again.
You said what now?
Your answer to 40 should start with a 4.
That's not good.
So here's, if you look on 40, let me give you a hint. I'm probably, typically if this goes south, is because you used the wrong moment of inertia. So on 40, you've got a solid cylinder, it has the same mass as a solid sphere, radius. The cylinder and sphere have the same moment of inertia about the centers. What is the sphere's radius? So on 40, here's what you want to do. You're going to set the two eyes equal to each other. Okay? So how do you find the moment of inertia of a solid cylinder?
1/2
So
or
1/2
mr squared.
1/2 mr squared, right? How do you find the moment of inertia of a solid sphere?
2/5 mr squared.
2/5 mr squared. Then it's just a matter of solving for it.
Could I just do math on? What's that?
Now conveniently, what happens to the mass?
How did I get 4/5 out
You
of
should
multiplying 5/2 in 1/2?
I think there's your problem.
That, yeah. Should
Yeah,
be
check
5
your math.
Should be 5/4.
Your answer to 34 is going to make a not so good GPA.
Like a
Not so good.
really bad.
I don't know, mine's kind of mid.
Like really bad.
Define mid.
Like a solid B student. With
Oh,
a
no.
couple A's.
Like this is a solid
Okay.
F student.
Hmm.
Yeah.
Solid C at best.
Oh,
Hmm.
never mind.
Now, let me give you a hint on 34.
What'd you do for
Okay.
2?
Let me give you a hint. So on 34, you're told that you have the axle of 500 grams rotating about a bar. That's a very specific moment of inertia that you have to look up on page, whatever that is, 201. So a spinning bar has a very, very specific moment of inertia. And if that's typically where it goes wrong, because you use the wrong moment of inertia. Also, on 34 and 35, make sure that you tell me which direction that is, which direction the moment of the angular momentum vector is pointing. Tough for me to say today. So remember, on the right-hand rule, so let's say you've got this wheel and it's spinning like this. Okay, so here's your axis. So your moment of inertia always points at a right angles to the angle of spin. So if this is spinning like this, I would wrap my hands like this, and the momentum vector would point into the page. If it was going like this, I'd wrap my hands like this, and the momentum vector would be pointing up out of the page. If it's like this, I'd curl my hand like this, and I would say it points to my right. If it's going like this, and I spin it the opposite way, then I would say the momentum vector is pointing to my left. Okay? Go on.
Does that mean if you have the momentum vector pointing up and you spin it fast enough, it will just lift off?
No, no, no. That isn't, that's not a force. Okay? That's just telling you the direct, the only thing that's gonna happen, the faster you go, the bigger it will become, but it's not gonna lift off. It's just gonna become more stable, because then it's gonna be harder to get that to tilt, because of the fact that it's more stable. So the bigger that momentum vector is, the more stable the spin is.
Oh, okay,
Oh.
okay.
Is that because it's like more force is being put into like this certain direction?
Well, it's just a bigger
So,
vector.
Yeah,
And
bigger,
and
a
that,
bigger vector.
yeah.
So
Which,
And it would
which
just
is
be-
why,
what makes it harder
which is
to
why if
determine.
I spin this really slowly,
Mhm.
it won't stay up. Because if I spin it really slowly, it's a very, very tiny momentum vector pointing up. So it would be like this. Or if I spin it really, really quickly,
34.
then that momentum vector still points up, and now it's a bigger momentum vector,
Mhm.
and it makes it more stable,
Okay.
which is how gyroscopes work.
It's like a discus.
Why am I getting 33? Instead of 34.
I got 26.
Okay. Anything else on the assignment?
Wait.
Make sure on 34 and 35 you have the numeric answers and you tell me the direction of the momentum vector.
For 34 and 35.
34 and 35.
Is the direction just like in relation to the picture?
In relation to like you.
Like,
Well, yeah, so if you look on
so
34,
like
okay?
34.
So here's this
would be
bar, right?
axle.
And it's spinning like this,
Mhm.
okay? So the bar is spinning in the plane of the page. So it's either gonna be like this, and it's gonna be out of the page, or it's gonna be like this, and it's gonna be into the page.
Okay.
So both of your answers on 34 and 35 are either into the page or out of the page. Cohen?
Charles threw the rod at you yesterday?
Yeah, I got a bruise.
Really?
No.
Yeah.
Ah.
But as far as Charles knows, I have a bruise.
Well, I'll see him second
I
book.
will-
So is
I
there any
will-
message you'd like for
Yeah,
me
he
to?
sounds like, man, you hit Burkham, see, he said he had a bruise.
Dude, I will tell Charles in third hour.
Yeah, just seriously tell him that. It's like, man, Burkham,
Bergham's
You have my
bruised
hardest
today.
dislike.
Yeah.
I
You
can't
bruised
believe
him.
I can't believe you bruised Bird.
yeah.
Did I even bruise you when I hit you in the chest with the sledge?
No, but I was sore for like 4 or 5 days. Yeah. Okay, anything else? Once, twice sold? All right, stop you on the camera.